Hello and welcome to this web seminar on Integrated Bridge Health Monitoring System. I am Daniele Inaudi, Chief Technology Officer for the Roctest Group, and would like to welcome you today to this online presentation. First, a few words about this web seminar and the tools we are using. You should hear my voice through your PC, speaker or headsets. And you can also ask questions about the presentation. On your right-hand side, you will find a panel which is marked questions, and you can write your questions in there. I will answer some of the questions at the end of the presentation directly, and other questions will be answered by chat or by email later on. Also, in the next few days, you will receive a copy of this presentation, including a link to listen to the presentation with narration again. And also, you will receive a paper which contains a summary and some details about what we will discuss today. Let's start with an introduction about structural health monitoring, and I like to do that by drawing a parallel with the health monitoring of our own body. We have a very good and functional monitoring system for our own body, and through the appearance of pain or discomfort, it tells us that something is wrong with our body. Maybe we don't know exactly what it is, but it's enough to prompt us to go to the doctor, and the doctor will carry out additional exams, take an X-ray, a blood shot, and based on his observation and based on what we have described about our illness, he will formulate a diagnosis and hopefully find a cure for our illness. A similar approach can be used for the monitoring of the health of structures, bridges for instance. In that case, the nerve system is paralleled by the monitoring system, which is a network of sensors that permanently monitor the vital signs of the structure and record any deviation from a predefined pattern. Again, the monitoring system should not be designed to monitor and answer any question, but should be enough to tell the owner if something important is happening on the structure. This makes monitoring complementary to the inspection or on-site destructive testing, samples, etc., taken from the bridge. And again, the owner or the engineer can combine the information from the monitoring system and from the inspection in order to have a better view about the health of the structure, and if needed, propose a repair of the structure itself. Monitoring can be useful during several phases of the lifetime of a structure, basically all of them, during the construction, in particular any critical stages of construction, during the testing phase, of course during the use of the structure, the service phase, during any action of refurbishing, maintaining, enlarging or strengthening the structure, or even during dismantling. We have been sometimes asked to monitor structures that were intentionally damaged to learn something about them in the end of their life. Installing a permanent structural health monitoring system brings several benefits to the owner. There are benefits related to discovering deficiencies in time. So a few structures sometimes present deficiency that cannot be identified by visual inspection or by modeling. In this case, structural health monitoring can help the owner to save money by taking action early on. So repair will be cheaper and will cause less disruption to the use of the structure if they are carried out in time and not when the damage has progressed so far that the repair becomes more complicated and costly. Also, for structures that are insured, the monitoring can reduce the insurance cost because, again, it reduces unknown and risks associated with the structure. In many cases, quite the opposite happens, so structures are in better condition than expected, and in that case monitoring allow to increase the safety margin without actually doing anything on the structure itself except monitoring it. So this can lead to take advantage of better material properties, so maybe your concrete has higher modulus that was used in the calculation. Also there are synergetic effects that can be used to extend the lifetime or the load-bearing capacity of the structure without compromising the safety. So this brings to the so-called controlled lifetime extension of structure, so that it's possible to postpone a repair or replacement of structure while making sure that the structure does not degrade further or quicker than expected originally. Another benefit of structural health monitoring is that it allows structural management. So it's possible to carry out maintenance on demand, optimize operation, maintenance and repair of structure based on reliable and objective data and not only on subjective inspection data. Also, the data can be integrated with structural management system to increase the quality of decision making to provide a reliable and unbiased information. At a time where anything seems to be connected to the internet, it's also quite natural that structures that are so expensive and so critical provide data continuously and are brought online. Monitoring also ensures the long-term quality of structures, so each quality policy requires that measurement and feedback are taken to make sure that the quality corresponds to the initial plan. By providing continuous and quantitative data, not only during construction but also during operation and in the long term, it's possible to eliminate hidden cost of non-quality. Monitoring also increases the safety of the structure, obviously by guaranteeing that it performs according to the original plans. And finally, monitoring is also a tool for research and increasing knowledge about the performance of structure, both in laboratory condition and in the field. And that can lead to cheaper, safer, and more durable structure in the future. So by getting a feedback from the structure itself, it's possible through a small investment at the beginning of the project to optimize the design and save money in the long term. I'm often asked how we justify the return on investment by installing a monitoring system. Obviously, there is a cost associated with a structural health monitoring system, so how is that cost paid back? I will now analyze two cases to answer that question. The first one is about bridges that are candidate for replacement. So imagine a user has a number of bridges, let's say for example 100 bridges that are defined as structurally deficient and need replacement or very major repair. And let's assume that replacing all of them without applying structural health monitoring would cost 100%. Let's also assume, and it's quite a reasonable figure, that the cost of structural health monitoring is 3%. This 3% includes the sensor, the installation, the management, and the analysis of the data. Also assume that only 20% of the bridges are found to be in much better condition than expected. Another 20% of the bridges are found to need rehabilitation with a cost that we estimate at 30%. And let's assume that the rest of the bridges, 60%, really needs replacement. So after the structural health monitoring, you conclude, okay, they're bad condition and they need to be replaced. If you calculate the total cost of applying a strategy of first carrying out a structural health monitoring and only after that decide whether the bridge should be replaced or not, then you find out that you have 3% cost, plus 30% cost in 20% of the cases, plus the full cost in 60% of the cases. And this brings to a total cost of 69% compared to the cost of 100% if no structural health monitoring is carried out. So by applying structural health monitoring with those very conservative assumptions about the health of the structure while monitoring, it's possible to save 31% about the replacement cost. So in this case, bridges that are candidates for replacement, the return on investment is very easy to demonstrate. On the next slide, let's see what is the case for a new structure, for example, a new bridge. In that case, again, we can assume the cost of structural health monitoring to be between 0.5% and 3% of the original or the construction cost of the bridge. And also, you can assume that operating a structural health monitoring system for 10 years will cost between 2 and 5% of the structure cost. How is this cost paid back? There are several ways. The first interesting one is that if any hidden defects are in the structure and they can be discovered early, then they will be repaired at the cost of the contractor because they will follow under the warranty of construction. So this alone is a good enough reason to invest in structural health monitoring. Another case is discovering and repairing error during the construction. We have seen this a few times, that if you discover a problem when the building site is still operational and you have all the equipment on site, it is much cheaper for the owner but also for the contractor to correct any problem immediately rather than discovering it 5 years later and having to restart a big building site that has been removed in the meantime. Also ensure quality by checking. It's quite human, but if you know that someone is watching, usually the quality of the work it's improved. And finally, reduce cost of future repair and maintenance by providing repair and maintenance only when they're needed and not based on a predefined schedule. Now I will switch to the main topic of this presentation, is to present a methodology to design and deploy a structural health monitoring system. We have developed a methodology that is based on 7 steps. I will first list them here and then we will have a look in more detail at each one of them. Step 1 is identify structure needing monitoring. Step 2 is to acquire information on probable degradation mechanism and carry out a risk analysis in cooperation with design engineers and owner. Step 3 is to establish what are the expected responses to those degradation. Step 4 is design a structural health monitoring system to detect such condition and select the appropriate sensor to do that. Step 5 is to install and calibrate the system. Step 6 is to acquire and manage the data. And step 7 is to assess the field data. Let's now have a look at each of these steps in more detail. First step, identify structures needing or benefiting from structural health monitoring. Of course, it would be nice for me to say that all structures need structural health monitoring, but experience has shown that some of them can have more benefit from structural health monitoring. These are in particular new structure that include some innovative aspects in terms of material, construction procedure, shape, location, etc. Also new structures with unusual associated risks or uncertainties. For example, geological condition, an elevated seismic risk, meteorological risk like typhoons, for example, a particularly aggressive environment from the chemical point of view, any vulnerability during construction, delicate construction phases, and also when there are doubts about the quality of the materials used and the workmanship. Also, other good candidates for structural health monitoring are those structures that are critical at a level. So a very important bridge, maybe not by size or risk type, but a bridge that is important for linking two areas where people must really travel on that bridge or a tunnel in a similar condition. Also, new or existing structure which are representative of a larger population or identical and similar structures. So, for example, a highway overpass might not be a very interesting or challenging structure itself, but if there are 20 similar structures on that highway, monitoring one of them can lead to information that can be applied to the other one as well. Also, we have already talked about existing structures that present known deficiency or very low rating, and also structures that are candidates for replacement or any major refurbishment works. Once we have identified the structure that we want to monitor, we can move to the step 2, which consists in carrying out a risk analysis. The structural health monitoring system designer, the design engineer or the engineer in charge of structural assessment, and the owner must sit together and jointly identify the risks that are associated with a specific structure and also their probability. So they must say what can happen possibly to that bridge, and is this event an high probability, usually not, a medium probability, a low probability, or a very low probability. So a seismic event, for example, will have higher probability in a region with known seismic activity and lower risk in another one. Similarly for corrosion in a coastal or high mountain bridge where chlorine exposure is critical, that will have higher probability than a bridge in the middle of the desert, for example. The risk analysis will lead to a list of possible events and degradation that can possibly affect the structure, their impact, and their probability. So at the end of step 2, you will have a list of risks that must be addressed by the structural health monitoring system. This allows us to move to step 3, which is to identify the responses of those risks. So what will happen in reality to the structure if one of those risks become a reality. So for each risk, we will associate one or several responses that can be observed either directly or indirectly, and we will also try to quantify the expected responses. So for example, you could say if that event happens, the bridge will tilt by so many degrees, or the corrosion front will go inside the structure and will start corroding the rebars. Also, it will be useful to identify the location that might be affected by that risk if they are, for example, not affecting the structure as a whole. And finally, the different risks can be categorized whether they are better addressed by inspection or by structural health monitoring. There are some events that are easier to detect with sensors and others that are easier to detect by visual inspection. So at the end of that step, we will have a list of responses and also how to address them. And this allows us to move to step 4, which is really the design of the structural health monitoring system. Unfortunately, sometimes people start at step 4, so they design a monitoring system, maybe a very nice one, very high technology with nice sensor, but maybe it's not measuring the right parameters. So that's why it's important to start with the first 3 steps and move to step 4 only when you have the list of risks and the list of responses that are expected. At that time, you can select the appropriate sensor and technologies, consider the required lifetime in terms of structural health monitoring system, how long it must be operated, and also the available budget. And if there is a limit in the budget, as it's usually the case, you can start addressing the higher risk or the more important risk with higher probability associated and move down the list until the budget allows it. Also, it's important to consider reliability and redundancy, which sensors are very critical, and maybe we have to plan to have certain redundancies, so I have more sensors so that if some fail, there will still be enough to carry out the analysis. And also we have to define if the monitoring system must operate during 1 year during a critical construction phase or must operate for 50 years. This will lead to different designs of the monitoring system. It's also a time to define details about the installation, how to install the sensor, when to install the sensor during the construction period, and also to define a schedule of delivering the sensor, installing them, qualifying them, putting them in service, etc. Next step, installation and calibration. Obviously, we have to install, test, verify that the installation was carried out according to the specification. This usually terminates by a site acceptance test, where the owner verifies that the system has been installed correctly and everything is working according to the plans. Step number 6 is the data acquisition and management. It is important, of course, to operate the system in a way that the data is stored and can be easily accessed and analyzed. That's why we suggest to use a database approach. So we have developed a database system that we call SDB. It's an open standard that allows the data from any monitoring system, from the Rocktest group, but also from third parties, to write all the results of monitoring and additional information about the calibrations, about the interventions, about the location of the sensor into a single database that will contain all the data. Also, we have to document intervention and structural lifetime events. So document what actions have been carried out on the structure, what happened around the structure itself. All this information can also be integrated into the SDB database. So the database will also act as a kind of link between the hardware, the sensors, the data acquisition system, and on the other side, the software that is used to manage, display, and publish the data. Step 7, data assessment. This can be a difficult task if the monitoring system is not designed properly. Sometimes people tell us, oh, we have installed this monitoring system, everything is working, but I have so much data and it's in the database and that I don't know what to do with it. However, if you follow the previous steps, this becomes much easier because you already know what responses you are expecting, and if you observe those responses, you will be able to understand what risks have materialized. So by analyzing the responses of the structure, the engineer can identify if any of the foreseen risks and degradation have appeared. Also, it's important to establish beforehand what to do if a degradation appears. There are degradations that don't need an immediate action and others that require maybe immediately to stop the traffic and do something. So this is quite important to define a procedure. So if a warning is generated by the structural health monitoring system, we know how to react and how to handle that. Of course, analyzing the data, further doubts might arise, and in that case, that will prompt to further investigation, further inspection, maybe installation of other sensors to better understand what is happening. And the way of providing the data to the user will be through alerts and warnings or through periodic reports about the state of the structure. This was a general introduction about the methodology to develop a structural health monitoring system. Let's now have a look at the specific case of bridge structural health monitoring. There are, of course, many different types of bridges. Here I have listed the most common one: concrete beam bridges, steel beam bridges, concrete cantilever bridges, arch bridges, and the major bridges like cable-stayed and suspended bridges. Each of these categories presents some general risks that we can somehow generalized by type of structure, but of course each specific structure might also have its own specific risks associated with the location, with the specific design details, etc. We have prepared a table that for each type of bridge identifies which are the most important or common risks and uncertainty. So for example, here in the table you can see the first line says, okay, the correspondence between finite element model and real behavior, it's generally an issue of medium importance for all type of bridges. If we look on the other end at the dynamic response to traffic, wind and earthquake, these are of course more important for large bridges like cable-stayed and suspended bridges, and also for steel bridges because of the fatigue analysis, but are less of an issue for concrete bridges, for example. I will not go through this table in detail, but you will receive it in the next few days, so you can have a look at all the classification that we've carried out and maybe comment if you agree or if you have a different idea on that. The next step, as we mentioned, is to select what sensors are appropriate for analyzing a specific risk. Here is a list of typical sensors that are or can be considered for monitoring structures: local strain sensor, average strain, deformation sensor, temperature, corrosion, displacement, settlements, tilt, sensor measuring environmental condition, taking images of the structure, analyzing movement, vibration, localized loads, pressure, water pressure, etc. So there are several different sensors that can address different risks. And again, to help in making that link, we have prepared a table that lists the different risks that we have identified in the previous table, what is the common response or consequence, and what are the proposed sensors to monitor it. So for example, if you look at the second line, if the risk is related to the dynamic strain generated by traffic, wind, earthquake, or explosion, the expected response is strain, fatigue, or cracks. And this can be identified by local strain sensor, vibrating wire gauges, fiber optic sensor, dynamic data acquisition system, or a distributed fiber optic sensor to detect new cracks, or crack meter to measure crack opening of existing cracks, and so on. So following those two tables, you can first identify the risks, then the consequences, and then the sensors that can be used to address them. Again, you will receive the complete table in the document that we will send in a few days. To conclude the presentation and make it maybe a little less dry and theoretical, I would like to go through a real example. It's an imaginary cable-stayed bridge, so any resemblance to a real bridge is a pure coincidence. It's a new structure in the design phase, and the structural monitoring system design is based on data that we have received from the owner and the design engineer. The bridge itself, again, it's a hypothetical bridge. It's a cable-stayed bridge with two spans. It's an unsymmetrical bridge with spans of 92 meters and 51 meters and a deck width of 24 meters. And the structure includes a longitudinal deck, which is pre-stressed concrete, and a steel tower. Also, the bridge is designed to work as an integral structure. So step one, it's finished. We have defined which bridge we want to monitor. Step two is risk analysis. So by discussing with the structural engineer and the owner, those risks have been identified. First risk is a force redistribution among the stays due to traffic, due to temperature changes, and long-term effect. So for example, change in temperature might lead one state to take more load and the neighboring state to take less load. The stiffness of the deck, which was considered very stiff, also induces a strain redistribution among the states, but also within the deck itself. Also, there were some doubts about how the shear strain are transmitted at the deck joints, and also how the strain is transferred from the forward stays to the backward stays in the pylon itself. There are also some risks associated with corrosion, in particular at the foundations that are in the sea and at the anchor points, and finally some doubts about the stability of the foundations themselves. Step 3 was to identify the expected responses of the structure to those risks, and the expected response were to have a redistribution of forces among the stays, a change of strain in the deck and the pylon, a tilt of the pylon, a global movement of the bridge, so deck movement and pylon movement, and corrosion of the concrete. So these have been identified as the expected responses. And based on that, we can move to step 4, which is to propose an instrumentation system. So in that case, we have selected a SOFOMOS fiber optic strain and temperature sensor to address the measurement of strain and shear strain in the deck and pylon, to carry out modal analysis for dynamic response and to study the temperature distribution. We have proposed a SOFOMOS fiber optic tilt sensor to measure the tilt of the pylon and its bending. We have proposed vibrating wire load cells to measure the cable forces. We have proposed SenseCore wireless corrosion sensor to monitor humidity and corrosion in the concrete element subjected to corrosion. We have proposed RoboVac system to measure the global movement of the pylon and of the deck. And finally, a meteor station to measure wind speed and air temperature, and so having an idea of the environmental condition in which the structure is operating. So you've seen in this simple example how all the first 4 steps have been carried out. In particular, we are also able to define where the sensor will be placed, how many of them, etc. So here's a list of sensor location, where to place them, etc. And it's now possible to also show that plan on a schematic view of the bridge itself. So here you can see an image of the bridge where we have depicted the location of the strain sensor, of the tilt sensor, of the corrosion sensor, the RoboVac sensor, and the force sensors installed on the bridge. In this case, I'm not able to show you steps 5, 6, and 7. The system should also, at step 5, of course, the commercial part comes into play, so we have to convince the owner that he really wants it, supply it and install it. Step 6 will be to acquire and manage the data, and step 7 to assess the measurement results. We have made other presentations showing in more detail that part of the installation, data management and analysis, so this is not really the topic of today's presentation. I wanted to really concentrate on the design phase. So this brings me to the conclusion of my presentation. Integrated structural health monitoring systems are based on a design methodology that leads to an optimal system configuration for a specific structure and available budget, and they supply actionable and useful information to the owner. They are based on a number of standard and well-proven sensor packages, but they can be adapted to the specific needs and condition of the structure. And leveraging on Rocktest's unique positioning as a global supplier of the most complete toolbox of sensing technology and solution, we can really propose an optimal system that includes the right sensor for the right application. And with this, I conclude the first part of my presentation. Again, I will ask you to ask any question that you would like by using the question panel on the right-hand side of your screen, and I will answer a few questions now if you're interested, or I can answer your questions later if you have other one. And with that, I thank you for your attention. Okay, I have a first question. It's about whether monitoring can be used for analyzing a structure after a fire. Yes, that's an interesting case. We had a few, or let's say one specific application for that. It's a case where indeed the condition of the structure is doubtful, and installing a monitoring system can help to identify whether the structure is still in good condition and what type of repair can be carried out on the structure. So yes, fire is a kind of degradation that can affect the structure, much like the aging or the corrosion or other type of degradation. Another question is about how often we have used that methodology. This is indeed a relatively recent procedure in terms of formalizing it in those steps, but it's been many years where we have started this more systematic approach in which we don't just propose sensors, but we really identify the needs of the structure and how the sensors can be used. I think that having now formalized those procedures, it makes it more easy also to communicate between SMARTEC, our local partners, distributor integrators, and the end customer, and make the process of designing and communicating the usefulness of a monitoring system easier to for all partners. Okay, with this I will stop the presentation here, and I will answer the other question directly with the chat. So thank you very much for your attention, and I hope to see all of you again for the next web seminar. Bye-bye.